What is the Titius-Bode law?
The Titius-Bode law was developed by German astronomer Johann Daniel Titius, 1729 to 1796. Titius's idea was brought to the forefront by German astronomer Johann Elert Bode, 1747 to 1826. The law actually represents a simple mathematical rule that allows one to determine the distances, also called the semi-major axis, of the planets in astronomical units. It is determined using the equation A equals 0.4 plus 0.3, 2n, in which n is an integer and a is the astronomical unit. Interestingly enough, most of the planets and even the asteroids in the asteroid belt adhere to the law. The only exception is Neptune, the second to last planet in our solar system.
What are the various methods of keeping time?
There are three basic methods of keeping time in common use today. They include time based on 12-hour intervals, AM and PM, a 24-hour clock, and coordinated universal time clock, called UTC or Zulu time. All of these have to do with simple mathematics, mainly addition and subtraction. A 12-hour clock, using the 12-hour interval concept, is familiar to most of us. It represents half a day, 24 hours divided by 2. The abbreviations AM and PM terms that originated from the use of longitudinal meridians are used to differentiate between the morning and afternoon hours. The term meridian, from the Latin meri, a variation of medius, or middle, and diem, or day, once meant noon. Thus, the time before noon was called ante-meridiem and after noon was called post-meridiem. They were eventually shortened to AM and PM, respectively. Whether the terms are capitalized or not is not an issue either, as both are used in texts. The 24-hour clock is, naturally, divided into 24-hour increments. It is commonly used by the military and other government agencies throughout many countries. UTC, or Coordinated Universal Time, the letters are not a true abbreviation, but a variant of universal time, is equivalent to mean solar time at the prime meridian. 0 degrees longitude, formerly expressed as GMT, or Greenwich Mean Time. The change was done to eliminate using the name of a specific location in an international standard. Other names for UTC are World Time, Zulu Time, and Z Time. UTC should not be confused with UT, or Universal Time. The basis for the coordinated broadcast of time signals, counted from 0000, or midnight.
What are some examples of mathematical models used by chemical engineers?
There are numerous examples of how mathematical models are used by chemical engineers, too many to mention them all here. One good example is modeling crystal growth. Liquids from water to molten metals become crystalline solids as they are cooled. Engineers can mathematically design software that helps in the manufacture of superior crystalline growth, especially for electronics and other industries. These improved crystal forms advance the quality of electronic hardware, including computers, and help engineers design better alloys for a wide range of applications.
How does population dynamics use mathematics?
Population dynamics combines observations and mathematics, especially the use of differential equations. For more about differential equations, see mathematical analysis. For example, to determine what the population of a certain country will be in 10 years. Scientists use a mathematical model commonly called the exponential model, or the rate of change of a population as it is proportional to the existing population. For more about population growth mathematics and the environment, see below.
How do astronomers determine the distances to the stars?
Relatively nearby objects beyond the solar system appear to shift position relative to more distant objects as the Earth moves from one side of the Sun to the other, a phenomenon called parallax. You can use parallax to determine the distance to stars. As long as these stellar objects are within a few dozen light-years of Earth. More distant objects in the sky do not change their position. Enough as the Earth orbits from one side of the Sun to the other. First, measure the position of the star in the sky, then measure it again in 6 months when the Earth is on the opposite side of its orbit. If the distance A and the angle AC are known, as seen in the diagram below. Using trigonometry, C can be determined as A/cos AC.
What is the component of a vector?
A component of a vector is one with n numbers in a certain order. It is usually listed as x1, x2, xn, in which the numbers within the parentheses are called the components of the vector. Logically, an infinite number of vectors can have the same components. For example, if the components are 3, 4, we know there are an infinite number of pairs of points in the plane with x and y coordinates whose respective differences are 3 and 4. All these vectors are parallel to each other, equal, and have the same magnitude and direction. Therefore, any vector with components of a and b can be said to be equal to the vector a, b.
What is numerical analysis?
Numerical analysis is a branch of applied mathematics that studies certain specialized techniques for solving mathematical problems. It employs mathematical axioms, theorems, and proofs, and often uses empirical results to further analyze or examine new methods.
When was quantum mechanics developed?
There was not one major year in which quantum mechanics was developed, or even one major scientist who proposed the idea. This modern theory of physics evolved over about 30 years, with many scientists contributing to it. Beginning about 1900, Max Planck proposed that energies of any harmonic oscillator, such as the atoms of a black-body radiator, are restricted to certain values. Mathematics came into play here, too, with each value an integral multiple of a basic, minimum value. Planck developed the equation E equals hv, or h times nu, in which E, the energy of the basic quantum, is directly proportional to the v, the frequency of the oscillator, multiplied by h, or Planck's constant, 6.63 x 10 to 34 joule-second. From there, mainly with the use of rigorous mathematics, others expanded or added to Planck's idea, including German scientist Albert Einstein, 1879 to 1955, who explained the photoelectric effect. New Zealand-born British physicist Ernest Rutherford, 1871 to 1937, and Danish physicist Niels Bohr, 1885 to 1962, who explained both atomic structure and spectra. Austrian physicist Erwin Schrödinger, 1887 to 1961, who developed wave mechanics, and German physicist Werner Karl Heisenberg, 1901 to 1976, who discovered the uncertainty principle. Out of these studies came quantum mechanics, in the 1920s, quantum statistics, and quantum field theory. Today, quantum mechanics and Einstein's theory of relativity form the foundation of modern physics. These theories continually change or are modified as we get closer to understanding more about the physics and mathematics of our universe.
What is the longest span of time measured on the geologic time scale?
The longest span of time measured on the geologic time scale is the Precambrian era, also called the Precambrian Eon. It represents the time between 4.55 billion years to about 544 million years ago, or about 7/8 of the Earth's history. This time period includes the beginning of the Earth's formation, its cool down, its crust's formation, and, within the last billion years of the time period, the evolution of the first single-celled to multi-celled organisms. The demarcation of 544 million years ago represents a burst in the evolution of multi-celled organisms, including the first plant and animal species.
Is there such a thing as a perfect number?
Yes, there is such a thing as a perfect number, but it is not what we think of as true perfection. To mathematicians, perfect numbers are somewhat rare. They are defined as a natural number, or positive integer, in which the sum of its positive divisors, or the bottom number in a fraction that divides the number to equal another whole number, and includes 1 but not the number itself, is the number itself. For example, 6 is considered a perfect number because its divisors are 1, 2, and 3, or 1 plus 2 plus 3 equals 6. The next perfect numbers are 28, 1 plus 2 plus 4 plus 7 plus 14. 496, 8128, 33,550,336, 8,589,869,056, 137,438,691,328, 2,305,843,008,139,952,128, and so on. Larger and larger perfect numbers are still being discovered. Especially with the help of today's faster and more memory-packed computers.
What is computational sociology?
Computational sociology is a branch of sociology that uses computation to understand social phenomena. It takes great advantage of statistics to determine trends in data, and uses computer simulation in the construction of social theories. It is also referred to as the study of social complexity.
What is metamathematics?
Metamathematics is the study of mathematical reasoning in a general and abstract way, usually by trying to understand how theorems are derived from axioms. Thus, it is often called proof theory. For more information about axioms, see below. It does not study the objects of a particular mathematical theory, but examines the mathematical theories themselves with respect to their logical structure. Metamathematics is also used in logic to study the combination and application of mathematical symbols. This is often referred to as metalogic.
What science fields use an abundance of mathematics?
The sciences that are heavy users of mathematics are the so-called physical sciences, including physics, chemistry, geology, and astronomy. These scientific fields are often contrasted with the natural or biological sciences. The physical sciences analyze the nature and properties of energy and non-living matter, and they often need the help of mathematics to determine the complex relationships between their interactions.
Who is sometimes called the first programmer?
Any of the first programmers in this case, of a calculating machine was Ada Augusta Byron. 1815 to 1852, also known as Ada King, Countess of Lovelace. The daughter of Lord George Gordon Noel Byron, 1788 to 1824, the famous English poet. Inventor and mathematician Charles Babbage met Ada Byron around 1833. While still working on his difference engine. Her interest was reportedly more in his mathematical genius, not his machines. Besides her admiration for him, Ada Byron also put Babbage's name on the computing map, writing up most of the information about his work, which was something Babbage supposedly could not do as well. For example, she translated an 1842 account of his analytical engine, written by French-born Italian engineer and mathematician Luigi Federico Menabrea 1809 to 1896, from French into English. Babbage was so impressed that he suggested she add her own notes and interpretations of the machine. With his encouragement, she added copious notes, describing how the analytical engine could be programmed, and wrote what many consider to be the first ever computer program. Her account was published in 1843. She was also responsible for the term do loop in computer language, a part of a program she called a snake biting its tail, and for developing the mnemonic technique that eventually helped simplify assembler commands. Ada Byron's life deteriorated after writing her notes because of family difficulties, gambling debts, though not her own, the lack of a scientific project to work on, and probably the fact that none of her friends were as deeply and intuitively involved in mathematics or the sciences as she was. Babbage was no help, either, having his own difficulties, including his ongoing attempts to obtain governmental funding for his analytical engine. In 1852, at only 37 years of age, Ada Byron died of cancer, but she was not forgotten. She was remembered and honored in 1980 when the Ada programming language was named after her.
What does this mean for our calendar?
It is already known that our calendar and the length of a year were only off by 24 seconds. 0.00028 days, in 1582, a very small discrepancy that will eventually be noticed. But when you add in the slowing down of the Earth's rotation, it will make the year even shorter. In fact, since 1582, the year has decreased from 365.242222 days to 365.24219 days, or an actual decline of about 2.5 seconds.
What are the basic Roman numerals and how are they used?
There are only 7 basic Roman numerals, as seen in the following chart. Number Roman numeral 1 I5 V10 X50 L500 D1000 M. There are many rules, of course, to this method of writing numerals. For example, although the way to write a large number like 8000 would be M, This is very cumbersome. In order to work with such large numbers, one rule was to write a bar over a numeral, meaning to multiply by 1000. Thus, 8,000 would be 8 equal to our Hindu Arabic number 8 with a bar over the entire Roman numeral.
Is it easy to figure out the size of a distant object?
Yes, it is often possible to figure out the size of distant objects, as long as they aren't too small. The key is in knowing the distance to the object. For example, if someone holds a nickel at arm's length and then has someone hold the nickel 200 yards away, the coin may appear to be smaller, but its size really hasn't changed. If a person knows how large an object appears to be, and how distant it is, they can work backward to determine the true size of the object. Simply put, this is also how astronomers work out the size of distant objects in outer space.
What were the problems with the Egyptian number system?
The Egyptian number system had several problems. The most obvious being that it was not written with certain arithmetic calculations in mind. Similar to Roman numerals, Egyptian numbers could be used for addition and subtraction, but not for simple multiplication and division. All was not lost, however, as the Egyptians devised a way to do multiplication and division that involved addition. Multiplying and dividing by 10 was easy with hieroglyphics. Just replace each symbol in the given number by the sign for the next higher order. To multiply and divide by any other factor, Egyptians devised the tabulations based on the 2 times tables, or a sequence of duplications.
Where does most of our knowledge of Egyptian mathematics originate?
Most of our knowledge of Egyptian mathematics comes from writings on papyrus, a type of writing paper made in ancient Egypt from the pith and long stems of the papyrus plant. Most papyri no longer exist, as the material is fragile and disintegrates over time. But 2 major papyri associated with Egyptian mathematics have survived. Named after Scottish Egyptologist A. Henry Rhind, the Rhind papyrus is about 19 feet, 6 meters, long and 1 foot, 1/3 meter, wide. It was written around 1650 BCE by Ams, an Egyptian scribe who claimed he was copying a 200-year-old document. Thus the original information is from about 1850 BCE. This papyrus contains 87 mathematical problems, most of these are practical. But some teach manipulation of the number system, though with no application in mind. For example, the first 6 problems of the Rhind papyrus ask the following. Problem 1. How to divide n loaves between 10 men, in which n equals 1, in problem 2, n equals 2. In problem 3, n equals 6, in problem 4, n equals 7, in problem 5, n equals 8, and in problem 6, n equals 9. In addition, 81 out of the 87 problems involve operating with fractions, while other problems involve quantities and even geometry. Rhind purchased the papyrus in 1858 in Luxor. It resides in the British Museum in London. Written around the 12th Egyptian dynasty, and named after the Russian city. The mathematical information on the Moscow papyrus is not ascribed to any one Egyptian, as no name is recorded on the document. The papyrus contains 25 problems similar to those in the Rhind papyrus, and many that show the Egyptians had a good grasp of geometry, including a formula for a truncated pyramid. It resides in the Museum of Fine Arts in Moscow.
What is the difference between the Earth's sidereal and solar days?
The difference between the Earth's sidereal and solar days has to do with angles and the Earth's rotation. The mean solar day is equal to 24 hours, or the average of all the solar days in an orbital year. The mean sidereal day is 23 hours, 56 minutes, and 04.09053 seconds. It is not exactly equal to a solar day because by the time the Earth has rotated once, it has moved a little in its orbit around the Sun. Thus, it rotates for about another 4 minutes before the Sun is considered to be back in exactly the same place in the sky as it was the day before. The actual divisions of geologic time are not arbitrary, or uniform. The larger divisions are based on major events that occurred sporadically over the Earth's long history. For example, the end of the Permian period, about 240 million years ago, was marked by a major catastrophe. Some scientists estimate that close to 90% of all species on the Earth died at that time, resulting in a major extinction event that may have been caused by huge volcanic eruptions or even a space object striking the Earth. The smaller divisions are usually based on specific local structures or fossils found within the rock. Most often they are named after local towns, people, and sundry other nearby associations.
How have computers been used to factor large composite numbers?
Computers have often been used to factor large numbers, and not just by number theorists having some fun. In fact, factoring such numbers has helped to test the world's most powerful computer systems, to promote designs of new algorithms, and in cryptography used by people who need to protect sensitive information on their computers. For example, in 1978 several computer experts proposed using the reconstruction of the prime numbers from the product of two large prime numbers as an encryption technique. This method of encrypting sensitive data soon blossomed. especially because of the needs of the military and banking industry. The public also reaped the benefit of this idea as it eventually led to encryption. Methods such as the public key encryption for banking and personal pages on the Internet.
What are the definitions of zero and non-zero?
Those who use the Hindu-Arabic numeration system are all familiar with the concept of zero, and its importance. The symbol zero represents a valuable placeholder. It is also the additive identity element of an algebraic system, when a number and its additive inverse add up to zero. And, finally, it is the starting point in measurements. The zero symbol is also called a cipher, no relation to sending secret messages. Or the symbol for the absence of quantity, although be aware that cipher can also mean any Hindu-Arabic numeral. In other words, zero is not, nothing, or, from the Old English, na-wit, meaning not na and thing-wit. Mathematicians also use the word non-zero to represent a quantity that does not equal zero. A real non-zero number must either be positive or negative. A complex non-zero number can be the real or imaginary part of the equation. For more information about complex numbers, see above.
What does iteration mean?
In most English texts, iteration means to repeat, and this holds true for mathematics. In the case of numbers, iteration means a procedure in which the result is fed back and the procedure repeated. In some instances, it is repeated over and over. For example, to find the square root of 39. You can use iteration or repeat a procedure to find the solution. Knowing that the solution must be close to 6, or the square root of 36, a number close to 39. One can divide 39 by 6, 39 sixths, and get 6.5. Next, average 6 and 6.5 to get 6.25, then iterate again. Dividing 39 by 6.25, 39/6.25, equals 6.24, the actual square root of 39 is 6.244997. One of the most obvious instances in which iterations take place is in a calculator or computer. For example, in order to get the square root of 39, as in the example above, a calculator or computer automatically uses iteration to calculate the answer to a certain decimal place. The more numbers in a procedure, the more iterations are needed. Which is why supercomputing has become such a great asset not only to mathematics but many other sciences as well.
What is the range of a set of numbers?
The range of a sample, or data set, is used to characterize the spread or dispersion among observations in a given population. as it is the distance between the highest and lowest numbers. In statistics, it is often, logically, referred to as the statistical range. Numerically, it is represented by the highest score minus the lowest score. For example, for the range of the numbers 34, 84, 48, 65, 92, and 22, the range is 92 22 equals 70.
What is a base in mathematics?
The term base has many meanings in the English language, including several that apply to the field of mathematics. When talking about sets, bases are the open sets whose union forms an abstract entity called a topological space. In geometry, the base represents the side of a polygon or polyhedron that is perceived as its bottom. When referring to an isosceles triangle, the base is the side that differs in length from the other two. Thus, the base angles include the side that is thought of as the base. Algebraists also use the term base to describe either the number used with an exponent to create a power, such as 34 equals 81, or to write the same number as a subscript to a logarithm, such as log 381 equals 4. For more information about logarithms, see algebra. One of the more familiar uses of the term base in mathematics deals with our numbering system, in which a base is a natural number whose powers are added to produce a specific number. For example, using 10 as a base, the number 2583.789 is actually 2x103 plus 5x102 plus 8x101 plus 3x100 plus 7x10 to 1 plus 8x10 to 2 plus 9x10 to 3.
What are computer codes and programs?
Mathematics is an important part of computers, because math is used to write computer codes and programs. The codes are the symbolic arrangement of data, or the instructions, in a computer program, a term often used interchangeably with software. The code, also called the source code, or just source, is any series of statements written in some programming language understandable to the user. This source code within a software program is usually contained in several text files. The program is the sequence of instructions, or computations, that a computer can interpret and execute. In other words, most programs consist of a loadable set of instructions that will determine how the computer reacts to user input when the program is running. The connection between codes and programs is often heard by students studying computer science or working professionals, and even in action movies and television programs. As in, I need to add more lines of code to the program.
How does one sample a population?
Sampling is the term used when one obtains a sample of a population. The number of members in the sample is called the sample size. As with most mathematical concepts, there are several types of sampling. Random sampling is a technique involving a group of subjects, the sample, from a larger group, population. It is a method that reduces the likelihood of bias. In random sampling, each individual is chosen by chance, with each member of the population having a known, but often unequal, chance of being included in the sample. Simple random sampling also involves a group of subjects, the sample, from a larger group, population, but in this case, each individual is chosen entirely by chance, with each member of the population having an equal chance of being included in the sample. In fact, each member of the population has an equal chance of being chosen at any stage of the sampling process. Independent sampling comprises samples collected from the same or different populations that have no effect on one another. In other words, there is no correlation between the samples. Stratified sampling includes random samples from various subgroups, also called subpopulation or stratum of the population, chosen to be representative of the whole population. It is often thought of as a better technique than simple random sampling. For example, if a sheep farmer wanted to determine the average weight amount of wool gathered from 3 types of sheep on his farm, he could divide his flock into the 3 subgroups and take samples from those groups. In cluster sampling, the entire population is divided into clusters, groups, then a random sampling is taken of the clusters. This technique is used when a complete list of the population's members can't be studied, but a list of population clusters can be gathered.
How is a dimension described in mathematics?
In mathematics, a dimension is the number of coordinates, or parameters, required to describe points of or even points on a mathematical object, usually geometric in nature. The dimension of an object is often referred to as its dimensionality. For more about coordinates, see elsewhere in this chapter. For more about dimensions and science, see Math in the Natural Sciences. Each dimension represents points in space from a single to multiple points. The concept of dimension is important in mathematics, as it defines a geometric object conceptually and/or visually. In fact, the idea of dimensions can even be applied to abstract objects that can't be directly visualized. Mathematicians most often display such dimensions on graphs using a single point. For example, x, to represent one dimension, 2 points, usually x and y, or an ordered pair. To represent 2 dimensions, and 3 points, usually x, y, z, for 3 dimensions. The 4, and higher, dimensional analogues of 3-dimensional objects. often retain the prefix hyper dash such as hypercube and hyperplane. The basic geometric structures of higher dimensional geometry, the line, plane, space, and hyperspace, all consist of an infinite number of points arranged in specific ways.
How do various disciplines use applied mathematics?
Depending on the discipline, researchers use applied mathematics in various ways. For example, some disciplines rely heavily on pure mathematics. Numerical analysis, a form of applied mathematics, is a field that uses pure mathematics to decipher partial differential equations and variational methods. For more information about numerical analysis, see below. For partial differential equations, see mathematical analysis. There are also areas of applied mathematics that overlap other fields of study. For example, there are mathematicians who use applied mathematics to study the structure of matter, especially the behavior of subatomic particles, a field that also overlaps the same types of studies done by subatomic physicists.
What is a geometric sequence?
A geometric sequence or geometric progression is a finite or infinite sequence of real numbers with the ratio between two consecutive terms being constant, called the common ratio or R. In this case, each term is the previous term multiplied by a given number. In a geometric sequence, the formula for the nth term, in terms of the first number and the common ratio, becomes n equals a 1 r n 1. Here the first term a 1, r is the common ratio, and the number of terms is n. For example, for the numbers 2, 6, 18, 54, 100, and 62, a 1 is 2, r is 3, and n is 5. The equation then becomes 2x 35 to 1 equals 162.
What are some applications of operations research?
Applications of operations research span a wide variety of fields, especially with regard to reducing costs or increasing efficiency. The following lists just a few examples: constructing a telecommunications network at low cost and top efficiency, especially when under high demand or after being damaged. Determining routes of school buses so fewer vehicles are needed, and designing a computer chip that will reduce manufacturing time.
What is a coefficient?
In an algebraic equation, a coefficient is simply a multiplicative factor. In the majority of cases, the coefficient is the numerical part, most often a constant, of the equation. Thus, it is called a numerical coefficient. For example, in 3x equals 6, the coefficient is 3, in dash 3x equals 6, the coefficient is minus 3. As the coefficient takes on the sign of the operation, terms such as xy may not appear to have a numerical coefficient. But it is a number that is not written, but assumed. Coefficients do not have to be just numbers. In the equation 5x3y, the coefficient of x3y is 5. But in addition, the coefficient of x is 5x2y, and the coefficient of y is 5x3. Coefficients are also seen in functions. For example, in the function f, x equals 2x, the 2 is the coefficient.
How is air density related to air pressure?
The expression thin air is actually a reference to the atmosphere's density, or how thick the air molecules are near the Earth's surface. In chemistry terms, density is merely the mass of anything, including air, divided by the volume the mass occupies. For example, the density of dry air at sea level is high, mainly due to the pull of gravity. In metric system terms, sea level density is about 1.2929 kg/m3, or about 1/800 th the density of water. But as altitude increases, the density drops dramatically. Mathematically speaking, the density of air is proportional to the air pressure and inversely proportional to temperature. Thus, the higher up one is in the atmosphere, the lower the air pressure and the lower the air density. There is somewhat of an athletic advantage to higher elevations, at least for players of such sports as football and baseball. Because the air density is lower, a ball thrown in high elevation places like Denver, Colorado, will travel even farther than a ball thrown in a close to sea level city, such as Miami, Florida. In fact, the air at the Denver Stadium allows balls to travel almost 10% farther.
Have computers had an effect on the field of statistics?
Yes, computers have had a definite effect on the field of statistics. In particular, personal computers, software such as spreadsheets and professional statistical packages, and other information technologies are now an integral part of statistical data analysis. These tools have enabled statisticians to perform realistic statistical data analysis on large amounts of data faster and cheaper than ever before. Statistical software systems are most often used to determine examples, understand existing concepts in the statistics, and to find new trends in statistical data. Most of the packages allow the data to be entered into the computer program. But the emphasis then switches to the statistician's ability to interpret the data. There are two well-known programs often used in statistics: the SAS and SPSS, both of which are commercial statistical packages. The SAS system is a statistics, graphics, and data management software package available for personal computers. It allows the desktop computer user to get the quality of results once reserved for users of mainframe computers. The SPSS, Statistical Package for the Social Sciences, is also a popular software package for performing statistical analyses. It enables the user to summarize data, determine if there are significant differences between groups, examine relationships among all the variables, and even graph the results.
How did Joseph Marie Jacquard's invention benefit calculating devices?
In the late 18th century, French weaver and inventor Joseph Marie Jacquard, 1752-1834, developed a practical automatic loom that wove patterns into fabric. It was controlled by a link sequence of punched cards. This in itself was a major advance in the production of textiles. But it would also prove to be a boon to calculating devices. Borrowing Jacquard's idea, both Charles Babbage and Hermann Hall Erith, see below, would use such cards on their own computing machines. The company that Hall Erith formed eventually became International Business Machines, IBM. A company that for 30 years promoted and benefited from mechanical punched card processing.
Why are the terms cardinal and ordinal sometimes confused in mathematics?
Cardinal and ordinal numbers are sometimes confused because they have two distinct mathematical definitions. The cardinal numbers in the numbering system should not be confused with cardinal numbers in set theory, in which any method of counting sets using a cardinal number gives the same result. Likewise, the ordinal numbers in arithmetic should not be confused with ordinal numbers in set theory. Such numbers, often called ordinals for short, are the order type of a well-ordered set. They are divided into two types, finite and transfinite ordinals. For more about sets, ordinals, and cardinal numbers, see Foundations of Mathematics.
Why are functions important to analytic geometry?
The intricacies of functions are important mainly because the function and the graph of all the points in a function is one of the basic foundations of analytic geometry. This becomes even more evident when trying to solve complex equations or equations with more than one variable. For example, when determining the solution to an equation, such as 3x plus 4y equals 8. The two resulting numbers called a set of ordered pairs of numbers is called a relation. In turn, a function then becomes a relation in which each first element, such as x, is matched exactly with the second element, such as y. In other words, a function can take on a definite value, or values. When certain values are assigned to other quantities or independent variables of the function. For more information about functions, see Foundations of Mathematics and Algebra.
What was the difference engine?
Because of its automatic sequential approach. The difference engine is thought of by most mathematical historians to be the precursor to modern computers. Johann H. Müller, an engineer in the Hessian Army, first developed the concept in 1786. His idea was to have a special machine that would evaluate and print mathematical tables by adding sequentially the difference between certain polynomial values. But he could not get the funds to build the machine. Müller's idea was soon lost before it was resurrected in 1822, when Charles Babbage obtained government funds to build a programmable, steam-powered prototype of Müller's device. For more information about Babbage, see below. Because of technical limitations, funding cuts, and Babbage's interest in a more advanced device of his own design, Müller's difference engine was only partially completed. Eventually, Swedish inventors George Scoits, 1785–1873, and his son Edvard, 1821–1881, would in 1853 build the difference engine, the first calculator with the ability to print.
What are the names given to regular polygons?
Polygons are classified according to the number of sides they have. A polygon with n sides is called an n-gon. The following lists some of the names of polygons, depending on the number of sides. It is also possible to substitute n-gon, when the name is not known, for example 14-gon or 20-gon. Some texts list a two-sided polygon as a digon, but this is only meant for theoretical mathematics.
How did mathematical analysis develop after the 16th century?
Ideas about mathematical analysis took a long hiatus after the Greeks. It didn't begin to grow again until the 16th century, when the need to examine mechanics problems became important. For example, German astronomer and mathematician Johannes Kepler, 1571–1630, needed to calculate the area of sectors in an ellipse in order to understand planetary motion. Interestingly, Kepler thought of areas as the sums of lines, a kind of crude form of integration. Even though he made two errors in his work, they cancelled each other out and he was still able to determine the correct numbers. By the 17th century, many mathematicians had begun to contribute to the field of mathematical analysis. For example, French mathematician Pierre de Fermat, 1601–1665, made contributions that eventually led to differential calculus. Bonaventura Cavalieri presented his method of indivisibles. One he developed after examining Kepler's integration work. English mathematician Isaac Barrow, 1630–1677. Worked on tangents that formed the foundation for Newton's work on calculus. Italian mathematician Evangelista Torricelli, 1608–1647. Added to differential calculus and many other facets of mathematical analysis. In fact, collections of paradoxes that arose through the inappropriate use of the new calculus were found in his manuscripts. Unfortunately for mathematics, Torricelli died young of typhoid. And, of course, the one name most associated with calculus, Isaac Newton, developed some of his most brilliant work during the 17th century.
What do these philosophies tell about the state of modern mathematics and logic?
Like many abstract and complex studies, philosophies come and go. Some are good, some seemingly on the mathematical fringe. But they also show us that there is currently no single philosophy that truly defines our mathematical and logic foundations, especially when it comes to combining both mathematical knowledge and the application of mathematics to physical reality.
How did early painters integrate mathematics in painting?
Early painters had a problem: how to represent the three-dimensional world on a two-dimensional canvas. Or, how to give paintings depth and perspective. Although perspective does follow mathematical guidelines, many early painters were able to incorporate perspective, or depth perception, intuitively. The idea of perspective flourished around the time of the ancient Greeks, who used a form of perspective to design certain architectural structures and even theatrical stage settings. But it is unclear whether they actually understood the mathematics behind perspective. One of the first to create the impression of depth by using certain rules was Italian painter, sculptor, and architect Giotto di Bondone, c. 1267–1337. But those rules were of his own devising and were probably not based on mathematics. Whatever the case, he clearly worked out a way to represent depth in space. And he came close to understanding linear perspective. But it took until the Renaissance before painters explored the science behind perspective. In the early 1400s, sculptor Filippo Brunelleschi, 1377–1446, made the first correct formulation of linear perspective using mirrors. He understood that there was a single vanishing point to which all parallel lines in a plane, or on his canvas, converge. He also understood scales, calculating the relationship between the actual length of an object and its length in the picture, depending on its distance in the painting. Writer and mathematician Leone Battista Alberti, 1404–1472, was the first person to write the rules of perspective in 1435. Using the principles of geometry and the science of optics. By 1450, artist and mathematician Piero della Francesca, 1412–1492, had written an even more extensive mathematical work on perspective, including concepts of art, arithmetic, algebra, and geometry. The writings of mathematician Luca Pacioli, c. 1447–c. 1517, or Friar Luca dal Borgo, who was also known as the father of accounting, see below, delved more into perspective, including in his book De Divina Proportion, which relied heavily on Francesca's work. The illustrations in Pacioli's book were done by none other than the famous scientist, painter, and Renaissance figure Leonardo da Vinci, 1452–1519, who was himself a great contributor to the study of perspective. Pacioli was one of da Vinci's teachers, and he instructed the eventual great master a good deal about proportion and perspective.
What are antiderivatives and antidifferentiation?
An antiderivative is often interpreted as the same as an indefinite integral, but they actually do differ in definition. Using the notations above describing the fundamental theorem of the calculus. See box text for definition of the fundamental theorem of the calculus. The function f, x, is an antiderivative of f, x, described as also equal to the integral of f, x. The actual process of finding f, x, from f, x, is called integration or antidifferentiation.
How do computer models attempt to predict the weather?
In general, computer models used to predict weather use around 7 equations that govern how the basic parameters temperature, pressure, and so on change over time in the atmosphere. Scientists call the study of how they can physically and mathematically represent all the processes in the atmosphere dynamics. In reality, everyone knows computer models can't perfectly predict the weather at this time. This is because of several factors, including errors in the initial conditions, or the observations the model gets to begin making its forecast, and errors inherent in the model. A computer model can't take into consideration all the factors controlling the weather. Long-term forecasts are even more inaccurate because these two errors are compounded mathematically over time.
How do astronomers determine the distances to other planets?
Astronomers need mathematics, of course, to determine the distances to the planets and satellites of our solar system. One of the first astronomers to work this out was Nicolaus Copernicus. See above, using simple observations of planetary positions. One of the earliest methods to determine such distances was to use the orbital period of a planet. This varies as the square root of the cube of the distance from the Sun. T equals kxr, 3/2, in which t is the time for one revolution. R is the distance between the centers of the Sun and the planet, and k is a constant.
What are some basketball statistics?
One of the main ways a National Basketball Association coach evaluates a player's game performance is by efficiency, which is determined by using the formula, points and rebounds and assists and steals and blocks. Field goals attempted, field goals made, plus, free throws attempted, free throws made, plus turnovers. Field goal percentage, FG%, is determined by the field goals made. FGM, divided by the field goals attempted, FGA. Finally, the free throw percentage, FT%, is determined by the number of free throws made, FTM, divided by the free throws attempted, FTA.
What is abstract algebra?
Abstract algebra is a collection of mathematical topics that deal with algebraic structures rather than the usual number systems. These structures include groups, rings, and fields. Branches of these topics include commutative and homological algebras. In addition, linear algebra and even elementary number theory. See Math Basics, are often included under abstract algebra.
The following lists some simple keywords and their corresponding operation. What are independent and dependent variables in algebra?
Variables can be broken down into independent and dependent variables. An independent variable is a quantity that increases or decreases, is variable, or that has an infinite number of values in the same expression. For example, in the expression x2 plus y2 equals r2, x and y are variables. A dependent variable is a quantity that varies but is produced by changes in the independent variable. In other words, the dependent variable's value is dependent on the independent variable. For example, in the expression f, x, equals y, x is the independent variable and y is a dependent variable. Because y is dependent on the value of x.
What is a number?
The term number can be defined in many ways, including a sizable collection of people or things, and even an indefinite quantity or collection. In mathematics, a number, or numeral, is usually defined as a symbolic representation of a specific quantity or place in a sequence. To most people, the most familiar numbers are 1, 2, 3, 4, 5, and so on.
What is the historical significance of the barleycorn in measurement?
The barleycorn, just a grain of barley, definitely had a significant historical role in determining the length of an inch and the English foot. For more about the inch and foot, see below. In addition, in traditional English law, the various pound weights all referred to multiples of the grain. A single barleycorn's weight equaled a grain, and multiples of a grain were important in weight measurement. Thus, some researchers believe the lowly barleycorn was actually at the origin of both weight and distance units in the English system.
How are spheres described?
A sphere in solid geometry is considered to be the set of points, or the skin of the sphere, in three-dimensional Euclidean space that are equidistant from the sphere's singular, central point. Or, more simply, a sphere is a perfectly round, three-dimensional object. The term sphere also extends into other dimensions. For example, a sphere in 2 dimensions is also called a circle.
What are variables in algebraic equations?
Variables are the symbols, usually a letter such as x or y, used in algebraic equations that represent an unknown number n on whose value a function, polynomial, and so on, depends. Variables remain unknown until the equation is solved, thus they are sometimes referred to as unknowns in an algebraic equation. It is not always easy to work with variables, as there are so many letters used throughout various equations. But in many mathematical and scientific texts, there are some variables that are customary to use.
What are some examples of matrices?
The dimensions of a matrix are the number of rows, horizontal numbers, and columns, vertical numbers. It is written as the rows first, columns second.
Who first developed set theory?
German mathematician George Ferdinand Ludwig Philipp Cantor. 1845 to 1918, was not only known for his work on transfinite numbers, but also for his development of set theory, which is the basis of modern mathematical analysis. For more information on set theory, see Foundations of Mathematics. His Mathematische Annalen was a basic introduction to set theory. Unlike most long evolutionary histories of mathematical subjects, Cantor's set theory was his creation alone. In the late 19th century, Cantor also developed the continuum hypothesis. He realized that there were many different sized infinities, further conjecturing that two particular infinities constructed by different processes were the same size.